Hello, I am a PhD student, Chongwon Yu, and today I'm going to share a brief introduction to statistical analysis. And the warning is that this includes a statistical analysis in high level with examples. So if you want a mathematical or theoretical details, please refer to publications or your closest statistic professor. Okay, so the contents will be an introduction to this statistical analysis and some tests for analysis, and then brief suggestion for visualization. Okay, so what is a statistical analysis? Let's say there is a person A and person B. And this A says, I slept 8 hours today, and person B says, I slept 5 hours today. What can you infer from this situation? 조은님, can you what can you infer?
No. So the left guy looks quite a bit happier, I guess.
Don't look at their face, their comments.
And maybe the second person watches some YouTube shorts.
Okay, you're assuming. What I want to say is that this information, what you can only say is that person A slept more than person B. Yeah, today. That's all you can really say from this. Now, let's say person A drank a single cup of coffee and person B drank 2 cups of coffee. And now what they say is that one person says he slept 8 hours straight, meaning that without waking up, and the other guy say 5 hours without waking up. Now, can you say that drinking coffee affects the quality of the sleep? You may want to say it because the person B with 2 cups of coffee slept less hours because than compared to a person A with a single cup of coffee. But this, just from this data, it's not really representative to summarize that the drinking coffee has some relationship with the quality of the sleep. We need more data. So let's say there are multiple people. Although they look the same, let's assume that they're different persons, and we have like groups of data now. So now maybe we can say it's safe to say that drinking coffee affects the quality of the sleep, but still there are a bunch of diverse data, and from this data we have to interpret if this really supports our hypothesis. Now here is when the statistical analysis takes role. So this is to analyze the gathered data and see if there is any patterns or insights within it. It's because, as you see before, there are various ranges of data, even from single source or group, such as even from a single person, there can be a various blood pressure depending on when you're measuring it. And there are various coffee consumptions even in our lab. So there are various seemingly unorganized data, and from that data we want to extract if there is any pattern. And so these kind of analysis is frequently used in following fields such as biology, chemistry, or medical science, economy, social science, and also human-computer interaction. So what about the field of computer graphics and vision, which we are in? The commonly used cases is to analyze user study results, such as a satisfaction ratings of generated images or user interaction time, etc. And as I read some papers, oftentimes I felt that the analysis has not been done thoroughly as it is done in HCI researches. And I understand because there are many other ways to prove or evaluate the performance of the suggested research, so that's the methodology. And so usually in the papers of computer graphics and vision, most of the times they just spread the questionnaires and calculate and compare the mean ratings. And so speaking of mean, we all know the basic statistics, right? Yeah. So I won't go much details of this statistics, but yeah, mean, median, mode, variance, and standard deviation is a common statistical terms that we use for analysis. And just a second. And this beautifully plotted graph is a bell-shaped curve, is what we want all of our data to be distributed like this. But in real life, it's not really like this. So, okay, here is the question. Is mean value a best representation of the data? So when we're doing a quantitative evaluation, almost all, I think, is based on a mean value of some complicated equation, such as root mean square error, mean absolute errors, etc. And yeah, it would be okay for such evaluations since they are conducting the experiments on like hundreds and thousands of data, but maybe sometimes it might not be the best way. For instance, we all know, I think we all heard of this example. So there's a UNC professor who told students that the average starting salary of geography major was $250,000, which is about what, 30억? I think. And geography major, which is 지질학, I think. So that's pretty high. And so how can this result happen? And maybe some already predicted, it's because he included a Michael Jordan salary in it. And that makes the average so high that the mean is not really a best representative of actual group, actual population. So this mean would be meaningful if the population follows the distribution of this bell-shaped curve, but apparently this example follows this skewed curve. So mean is kind of shifted to the right. So yeah, so this example is to show that directly comparing means of two or more data may not be probable, especially if the sample is small. Yeah, there is a paper about this, and if you're interested, you can go and read it. So people come up with a way to analyze this data other than just directly comparing the mean. And this statistical test focuses on either accepting or rejecting a hypothesis. It is to determine whether the relationship between the sets of data is significantly exist or not. And some of you who looked at this statistical test have seen lots of articles mentioning the null hypothesis. This null hypothesis, it says that there is no significant difference or there does not exist any relationship between the group. And most of us who are conducting this statistical test want to reject this. We want to say that there do exist a significant difference. In case there do exist a significant difference between the group who takes 1 cup of coffee and 2 cups of coffee. And you might also heard a lot of p-value. And p-value, which is also called probability value, tells how likely the data would have occurred randomly. So if the p-value is low, such as we usually set 0.05 as this boundary, it means that if the p-value is lower than 0.05, it means that the probability that the data occurred by a random chance is 5%. So the lower, it's better. And so if we ran a test and the p-value ends up smaller than 0.05, then we can say that the null hypothesis is rejected and that there exists a significant difference, or there exists a significant relationship between a sleeping hours of groups drinking 1 coffee and 2 coffee when related to the examples mentioned before. Okay, so there are various tests depending on the characteristic of data. Actually, there are more than these tests, but I brought a test that might be commonly used in our researches. So these tests can be divided based on the number of variables or number of groups to compare, and also whether the test should be parametric or not. So what is parametric and what is non-parametric test? Parametric tests assume that the data is from parametrized probability distribution, aka normal distribution. So we consider that like sample size greater than 30 kind of satisfies this assumption that it comes from the normally distributed population. Or even if it's not, we can conduct an additional test to assume that the data is from the normally distributed population. Also, you can use this when the comparing values are metric, not the relative measures. In case of non-parametric, it's a test that assumes the data is not from parameterized probability distribution. So this is usually the case when the sample size is small, or the comparing values are non-metric, which can also be ordinal, as it means that the values itself doesn't really hold anything. It can only be compared side by side relatively, such as the results of Likert scale. Okay, so let's first introduce the student t-test. I think you guys already know what this t-test is. And this t-test is often called student t-test because this paper is written by an author named Student, and there are some side stories about it, but yeah, I'll just pass. So this test is a parametric test and often used to compare the results of 2 independent groups. Oh, yeah. And this t-test from the t-test, t-value can be earned by dividing a noise from the signal. So what's the signal and what's noise? Signal is a difference between means, and the noise is a variability of the groups. So since this is this is a parametric test and assume that the population is normally distributed, you can say that the mean is at this highest peak of the population distribution, and we can assume that this is very representative. So here the signal means the difference of the mean, and the noise can be measured by the variance and divided by the number of samples. So the larger this variance is, the more likely that this t-value is getting smaller. So once you find the t-value, you can find a p-value based on this, based on the degree of freedom. So if the t-value is higher, let's say that the sample size, the degree of freedom is around 15, and we want to look for the p-value 0.05. And if you end up getting a t-value higher than 1.753, then you can say that the t-value is below 0.05 and that the null hypothesis can be rejected. Yeah, but these days, just program automatically calculates a p-value for you, so you don't have to calculate it by hand and look up for this chart. And you may also heard of pair t-test. This is for two groups that are not independent, which also means dependent of each other, such as the siblings who can share the information to each other, or each group consists of same members, but they are conducted two tests of different variable. Yeah. So in this case, for pair t-test, we are analyzing the differences or subtracted value between the result of two groups. So the equation that looked like this became like this, where D indicates a mean of the difference. Yeah. And okay, so move on. So for the parametric test that you can use for comparing two or more than two groups is a ANOVA, which is a short term for analysis of variance. And here you are comparing the variance between groups. And since it is comparing a variance of multiple groups, the null hypothesis only if the null hypothesis is rejected, then it only means that there do exist a significant difference within the groups we compared, but we don't know which groups are in that relationship. So in order to find that out, the post hoc test needs to be done and see which of the two shows such tendency or such significance. And from here, I won't go into details of the equations. I'll just briefly introduce to you what these are. Okay, so you might say, why not use multiple t-tests instead of using an ANOVA? And it appears that doing a multiple t-test ends up a better result. But there is a 함정. So conducting multiple t-tests results in an increasing chance of error. It's just like flipping a coin multiple times and counting the probability of it. So example, there are 4 groups to compare, and the probability of not obtaining a significant result, which we said that 0.05, actually it's at 0.01 minus 0.05, will be multiplied by the times of the comparison. So there are 4 groups. They're comparing 2 groups at a time. Yeah, it will result in 6 comparisons. So the equation will look like this, and it end up as 0.265, which is about 5 times greater than 0.05. This means that chance of incorrectly rejecting the null hypothesis increases, meaning that the chance of getting what we want, the answer we want, increases, but it's not a proper way. So that's why we use ANOVA instead of doing t-test multiple times. Now, for the non-parametric test, there are like counterparts for each of the parametric tests. So Wilcoxon-Ransom test is a counterpart of the t-test, and as you can see from its name, it's the test based on the order of the sample data. So also this is for the result from 2 independent groups. And the example case will be the case where you are comparing survey results where participants answered questionnaires in Likert scale. So since Likert scale, there can be 1 to 5, 1 to 7, 1 to 10, depending on what you choose. But anyway, this single value 1, 2, 3, 4, 5 doesn't really means anything explicit, like absolute. It's all for like, even from same person, this 3 or 4 can mean different to depending on how he feels or the conditions. So because it's very subjective and relative, that's why this rank-based analysis needs to be done. And you can use this test when the participants of each groups are not overlapped. So 2 different groups, independent. If you want to conduct a test that's from where same groups are conducting the test twice, we're evaluating things twice, then you have to go for the signed rank test. This is also related to this, so can be the counterpart of the paired t-test. And so it compares results between two dependent groups, and you can use it when same participants conducted the evaluation for each result. And I think this is mostly what we do in our lab. So yeah. And for analyzing the results from more than two groups, which you can use Kruskal-Wallis test, which is a non-parametric version of ANOVA. And since there are also more than two groups, you need to find out which two groups are shows that significant relationship. And for the post hoc test, the commonly used post hoc test is a Dunn's test with Bonferroni correction. So I use this all the times, and nobody really tackles it. So I think it's okay to use it. And so, yeah, I only mentioned a most commonly used way of analysis, but there are more tests and methods, such as multivariate analysis and chi-square test, etc. However, in our task, in like computer vision and computer graphics, I think you barely need to use this test. It's more used for like HCI, those fields. So that's why I didn't mention it. But if you need to know, there's another experts in this field. So you can ask her about this. And also, just to summarize what to choose, considering the following. So if the sample size is small, or the metric is ordinal, then go for non-parametric test. So if you use a Likert scale test, then go for non-parametric test. If you have a large sample size and the value is metric, then go for t-test or ANOVA. Pretty simple, right? And let me just briefly talk about visualization. Like there's 2 pages. So for visualizing the results related to this statistical analysis, there are also various ways. And you might want to consider what to show from this visualization. Like, do you want to show just a mean, or you also want to show standard deviation, outliers, and etc. If you're only going to show the mean, and we often use a bar chart to do so, but some reviewers might think this is not good enough. Like, why don't you just use a table instead if you're just going to show the mean? And I kind of agree with that. So if you want to show something more than that, then this using a visualization method with figures such as box plot would be much better than a naive bar plot. And this is an introduction. This is a good figure to show what the box plot indicates. So it shows outliers and the mean and where the quantiles of each the data located. So it shows more data compared to the bar plot. And yeah, I think it's much better choice. And also this diverging stacked bars can also be a good visualization, especially you want to visualize your results conducted in Likert scale, because it shows the portion of the how many, like the percentage of the results you got. And by doing so, you can like strongly suggest that our method received much more positive results than those comparing method. Like if you're just showing means, then you're just showing like it's really simple and you don't really know how many like. Anyway, yeah, so I forgot what to say, yeah. But anyway, what I want to say is that showing the proportion of what you got for each of this category would be a good way to visualize your results in Likert scale, and the reviewers might like it more than just a mere bar or box plot. Yeah, so this is it for my presentation. Do you have any questions? Feel free to ask.
Yeah, very nice presentation. I think this presentation refreshed my memory that I learned a long time ago. So in high level, this is a good summary. And then if you actually want to apply this, then what do you do? I mean, is there any specific software to apply all this, or do you have to use Excel?
Yeah, I didn't really go for the actual application because there's so many choices. I uses R and R Studio, but someone say like, who uses R these days? So I didn't really introduce it, but I really love R. But you can also use Pandas, or like Python supports lots of analytic tools and you can use it. Also, Excel provides nice statistic tool. I mean, Excel is perfect, but I just not used to it. So there are like online calculator doing this analysis. It's just that I think like the lab members are often frustrated to choose what analysis to start with. And I thought that this introduction is a good starting point for them to choose. And then once they choose it, there are so many ways to evaluate. So yeah, that's why I only brought up this.
Okay.
I have comment. You hear my voice? Yeah. For visualization, I heard that the box plot does not provide that much information about data distribution. I heard that, yeah. So I recommend to use box plot with 90% confidence interval, or represent the standard error instead of, showing the box plot, yeah.
The reason why I mentioned the box, 누구 말했어?
Not me.
Okay. Oh yeah, the reason why I mentioned box plot is because of the comment I got from the reviewer, that the reviewer were like, your bar plot doesn't mean anything. Why not use box plot? So that's why I kind of mentioned it.
Oh yeah.
Any other comments or questions? I mean, if you have any questions related to like analytic this analysis, you can ask. Like, no. Okay, then I guess this is it. Thank you for listening.